I think this one, because I think I introduced the mechanisms and reactions very early on, the challenging ones, and this one I think would be easy to follow. So I'm going to go back to this acidity. We're going to talk about the last reaction. So again, there's a lot of reactions for organic chemistry compared to your inorganic molecules. And again, this one would be addition. So A, B, C, D are addition reactions. Substitution is the last one. So the hydrohalogenation, again, you're adding an HX. This X can be a Cl or Br. And then you're just going to be populating or saturating the triple bond. Okay? So for example, I'm going to use this example, CH3, C triple bond CH. Okay, so unsymmetrical alkyne. And then if you're adding HBr, so the Br is going to go inside the triple bond, not on the terminal one. It's going to be here. So you're just saturating. So you're going to have two of this one. So C, C, H, and you just add Br. So you're going to have two Brs, Br, and then CH3. Okay, so just add. So it's an addition reaction. And then the same, if I have Br2s, so I'm going to have two of these. So I'm also saturating the triple bond. So you have a triple bond like this, and then you're just going to have Br, four Brs, Br, and then Br, and then you just have a single bond. Okay? Okay, so that's basically it. I can have HCl, Cl2, and it's going to be the same idea. So you make all the way to saturated RXs. Okay. So now when we do, so that is halogenation. This is hydrohalogenation. So it's pretty simple, nothing exciting. It's straightforward, simple. So when I showed you the contraceptive, right? It's actually a triple bond, but it's gonna go into the last one. Okay. So now let's do. I'm gonna go over a little bit of mechanism for C and D. So this is the letter C is hydration. So we are hydrating. That means that we add water. So I'm gonna use the same example, starting compound like this. Okay. So I'm just gonna do terminal one because if it's internal, you don't see a lot of difference in terms of the functional group. So I'm going to introduce a different functional group in here, and it's a ketone, so that's new for us, although we did this in the lab, right? Ketone and then an aldehyde, okay? So think about the water. So the condition is you have water, and then, so I'm gonna put this as red. So water, and then the catalyst at the bottom is mercury, sulfate, and then sulfuric acid. Okay, so, so you're adding water again. So I describe this, we know the terminology Markovnikov's product as opposed to non or anti-Markovnikov's product. So this one is the same. You add the Br inside, okay? And then this, so you kind of split the water, okay? So HOH, okay? So think about it this way, you're adding the same thing as your double bond, and then you're gonna make a bond between this carbon, O, C, and then H, okay? So when you do that, there is an intermediate, so CH3, C, it becomes double bond, CH, like this, right? Okay? So just make a bond. And then the triple bond becomes a double bond. This is not isolated, so you call it an enol, an alkene and an alcohol, enol. So in one carbon, you have a double bond and an OH, so it's referred to as an enol. This is an intermediate structure, which is not really isolated, but it goes forward to make so it undergoes a rearranges to form CH3, and then C, and then, so this becomes a double bond, and that becomes CH3. So, you can think about it, the water, H2O, right? This H goes, you see that? So the water is here, and then this is actually like this, HH. That is your H2O. But in short, it is the same as equal CH3C double bond O CH3. So this is now a ketone. Ketone has C double bond O as your functional group. So that's one way to convert an alkyne to a ketone. Okay? So I'm gonna go over the mechanism here. So the first is this is acting as a catalyst. I've never used this one because I try to avoid mercury. Okay, so what happens is the mercury sulfate, what do you think is the charge of mercury in this mercury sulfate? +2, okay?
Oh,
So it's +2 because sulfate is -2, okay? So because this is more crowded, the mercury is gonna attach on the side that is less crowded, on the terminal carbon, okay? So you're gonna make a bond. So what happens is this is your, so triple bonds and double bonds are acting as nucleophiles. So this would be your nucleophile, okay? And so it's gonna attack. So this bond is gonna attack your mercury, okay? So therefore, CH3, C, double bond, CH, and then you make a bond mercury sulfate -2. This mercury becomes what? +2.
Neutral.
It got 1 electron.
Negative.
+2. If it
+1.
+1, okay? It becomes +1, okay? So therefore, this carbon is, because this carbon, the bond here goes to make a bond to the mercury, therefore this carbon is a
Positive.
plus. So this is now a carbon-cut ion. So you have a carbon-cut ion,
I was about to say that.
okay? All right, so then the water attacks that carbon. So this is where the water comes in. So water, lone pairs, okay? So therefore it's gonna go in here, and then you make a bond to the water. So CH3, C, and then OHH plus, right? And then CH mercury +1, and then sulfate still around, okay? And then, so this is kicked out, the water, another water molecule picks this up, or you can just go like this, and then H plus comes out, and then you're gonna have CH3, COH, and then CH, and then the mercury in here. So the mercury acts to facilitate the addition or attack of the water onto that carbon. Okay? So then you have a sulfuric acid. So I'm I'm gonna go down here. So you have a sulfuric acid in here, so sulfuric acid is providing the proton, so you know the structure of sulfuric acid, okay? So now this H is gonna go to the carbon where the mercury was. So basically you're picking up this H and this comes out, it becomes OS, OH minus, all right? So then what happens to your mercury? So I made this pair of electrons pick up the H plus, right? Right? So we're gonna write the structure CH3, C, OH, and then double bond CH, okay? So I pick up one H, right? So the H went here, okay? And then what happened to your mercury? If I take this bond out and then I made a bond to the H, what happened to the mercury? It became what? Plus 2, right?
Yeah.
So it went back to plus 2. So you kind of recycled the mercury, made it plus 1, and then finally go back to a mercury plus 2, and eventually it becomes mercury sulfate, okay? So we have the other product, which is going to be mercury plus 2, and then you get back mercury sulfate. So this one became this again, okay? And this basically picked up the H plus, right? It became sulfuric acid again. So now we're back to this structure. So we're now here, okay? So, okay. So basically you're just going to rearrange. This is referred to as, so this is the enol, so it's called ketone or keto-enol isomerism. Specifically, this is referred to as tautomerism. Okay, so you get this structure. So again, how do you do that? So from this structure, you're gonna go like this to make a double bond, okay? So the same structure that I wrote in here, so it's like this. So, because you're making a double bond, you're gonna shift it here, and then pick this up, and then you have the CH3, and then C double bond now. So actually, this is the same as this. Okay? That's the final product. So this is the R group, I can change it to whatever length I want. I can make it a benzene, I can make it a cyclohexane, but that doesn't really matter because this is the one that we're focusing on. So that is your hydration and enol as an intermediate, and then you form a ketone as a product. Okay, so so I'm gonna do the second